Alrighty, what are we doing today? Oh yeah, lots of good stuff.
And threads.
Talking about threads and stuff. So, any questions first? I'm snarfing my lunch while I talk. So.
Did you decide on the chatter?
I think I'm going to do a chat program. Still haven't totally decided. Maybe one of these 11th hour decisions. All right, let's take a look at service learning project. So how many people are up to speed on their final project report?
Give or take.
I did this morning. About half the class was like, they were reading it like word for word because they hadn't looked at it yet. So let me just run through this really briefly, okay? This is due on Monday morning, Monday sometime. I don't remember what time I said it.
I think it's 8, I checked.
Is it 8 a.m.?
Yeah.
Okay.
8 a.m.
So Monday morning at 8. So there's no poster upload for spring quarter, right? There's still the fair that you demo at, but your final deliverable is this technical report, okay? And this is a full-on technical report, okay? It's not a checklist, it's not an outline, it's not a one-sentence answer to each question on the description. It's a full formal report, okay? Cover sheet, name, lab partners, project title, class, date, etc. And then, you know, introduction, overview, background, methodology, whatever sections you choose. The goal here is you can assume your reader is competent in whatever they need to be competent in. Java programming, digital circuit design, you know, whatever area, but they know nothing about your project, okay? So they understand whatever they need to understand to be able to do what you're doing, but they don't know any specifics about your project. This is about your project, okay? So I built an automatic yogurt stirrer so that, you know, at a pre-scheduled time, it will stir your yoga for you before you take it out of the fridge, so you don't have to stir it yourself and spill it, okay? So reader knows nothing about that. So I gotta tell them what it is that I'm doing and why I'm doing it. So these sections that I have listed, it's not like you've gotta have a section called objectives, but you've got to cover these kinds of things. So it's a service learning project. You're trying to solve some problem, right? And if you're making a game, you're not really solving a problem, but you are, right? Why are you making a game? Well, because you like playing games, because you want to take a break from studying, because other people want to have some way to entertain themselves, right? So objectives is just talking about like what is it I'm trying to accomplish, right? And to what degree is my project at this point accomplishing that, okay? And then you probably thought about different ways to do this. So alternative solutions are looking at basically results of whatever phase you were using to think about different approaches to the problem. Well, I thought about using Unity, and then I thought about just writing something in Java, and then I thought about making a card game, and you know, those kinds of things. And then I decided I was going to go ahead and I was going to use Unity and make a game that could run on Android. And I wanted to do that because blah, 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 right? It has good graphics, it means I can port it to my phone, etc., etc. Okay, and then probably the biggest part of your document is the solution specifications. This is basically where you describe what you did, what you came up with, right? So this is where you can put circuit diagrams, block diagrams, descriptions, code or references to code if you're storing your code in the cloud, flowcharts, pseudocode, right? Everything that describes how you came up with your solution, right? How you implemented it. And I've got it laid out here sort of from like higher level down to lower level. System diagram is the 40,000 foot view, inputs, outputs. Code and schematics is basically the lowest level view, right? So, but organize it and present it in whatever way you think efficiently lets somebody understand the inner and outer workings of your project. And then verification, right? So you're trying to make an automated yogurt stirrer. I can't say yogurt stirrer without saying yoga. Trying to make this automated stirring system, right? Does it work? How do you know? How do you test it? Well, I bought 12 yogurts and I put them in the fridge and I took them out and 10 of them were nicely stirred up and one had exploded and the other one vanished, right? So basically, what was your test plan, right? And how did it work? Is getting 10 out of 12 stirred a good success? Yeah, I consider that to be successful, you know, because I can always stir it by hand except for the one that vanished and went into a parallel universe. And then if you were to continue working on this, right, that's where future enhancements come in. And even if you don't plan to work on this, if you're never going to look at it again, right, if you were going to continue working on it, what would come next, right? Now that you've gotten to a certain point, what do you see as like opportunities for taking it further, right? Suddenly I realized I could stir all kinds of things, not just yogurt, you know, and I could use this to mix drinks for people, and I could sell this to a chain of you know, Hard Rock Cafe, and they could put it in all their bars and, you know, whatever. And then the usual lessons learned, but think about this here, right? This is something you've spent probably like 40 weeks on, maybe not continuously. But you know, 3/4 at Clark, you've been at least somewhat background thinking about this project, maybe working on it at different points during that. What have you learned? And it can be things that you learned in engineering, computer science. It can be things you learned more on the soft skills side about, like, you know, organization or time planning or goal setting or stuff like that. So you can kind of like do whatever you imagine in here. And then the last section is license terms, and this is really important to put in your document. The default license term for most people, you can just copy this in there, and it basically says anybody can do anything they want with this. Okay, so that's a completely open license. If you do not want that, just say license terms and say whatever you want, right? If you don't want it published, you don't want anybody else to see it, just say, do not publish this, do not let anybody else see it. Keep this private. It doesn't have to be legalese or anything like that. Just let us know so that when Izad and I are going through these and we're trying to figure out ones that we want to put up on the website, we see our license terms, we say, okay, we're not going to publish that on the website because they don't want that. So that's the only thing you have to put there. But if you do want it published, totally open, go ahead and put this in. Because if you want it published and we don't publish it, that's not a big deal. If you don't want it published and we do publish it, that's a big deal. Right? So this will tell us we can open source it. So any questions on SLP? All right.
I have a question about like licensing though. Like,
Okay.
if you have a version and you're totally cool with that version being like open source and like totally open for everybody, open license, but then like you make changes to it and the changed version you want it to be like private, does the like previous open license give people free range to like publish your new stuff or no?
That's a good question. So and this is a lawyer question. I'm not a lawyer, but I would think that if the previous version was open source and you changed something, right, and you said, you know, closed source, somebody cannot take that changed version and publish it or use it or stuff like that. But somebody could take the open source version if they make the same changes themselves, right? You've got no protection against that.
Yeah. Makes sense. Kind of skirts around the whole like at what point is it different?
And this is what IBM got into when they were trying to make clones of the PC. And they interviewed people and they had to ask them very specific bizarre questions to try to make sure that they had no previous knowledge of what was in the BIOS for PCs, because they wanted to come up with their own. Right? If you come up with something original, even if it mimics something else that's already out there, if you came up with it on your own, arguably it's yours. But that gets into weird areas. Like I say, it's a lawyer question. All right, anything else? So we were doing our voting thing on Friday, and we saw that we could make our votes come out kind of crazy by having this read, modify, write in an uncontrolled way, where two processes might be reading, modifying, and writing at the same time, and one of them could effectively nullify the effect of the other, and that cause unexpected behaviors. And so we have the synchronized keyword. And synchronizing basically lets somebody, it's like what we call a semaphore, right? So semaphore is like a signal flag. Imagine that near this piece of code there's a flag. And anytime somebody wants to execute it, they can take the flag. And as long as they hold the flag, they're the only one who can execute this. Okay, so you take the flag and you start executing your code. If somebody else wants to execute it, they look, the flag's not available, so they have to wait. In conflict resolution, there's a thing called talking sticks. If two people are trying to work through something, right, you have a stick, and the rule is you can only talk when you hold the stick. And you can talk for as long as you want, as long as you've got that stick, and the other person can't say anything. They have to listen to you. And then when you're done, you put the stick down, they can pick up the stick and they can say whatever they want. That's basically exactly how synchronized works. Okay, so the first thread that gets to this section of code will be able to pick up that flag, and now it's going to execute the code and nobody else can until this gets to the end of the synchronized block, right, which is right here, and then it releases the flag and now another thread can pick it up. So in this case, that flag is H. Okay, any object can be used as a flag, and H was an object that was passed when I constructed each voting machine. I passed it H, and H was just this random object called doesn't do anything, right? Could have been a string, could have been anything. So and then when I had this originally, and we ran this and the code broke, right? And the reason there is that the first thread gets one object, H. The second thread has its own copy of H because it's being constructed by the thread. And so those threads have different flags, right? And anytime that second thread wants to run this block of code, it looks and nobody's touching that flag, so it can take it and it'll run the code. So you're really not synchronizing. And similarly, if I synchronize on this, that's not really synchronizing either, because this is different for each thread. I can't do this because it's static. But if I was in a instance of a class here, I could pass this to each of the threads, and then each of the threads would be looking at the same object, and that's a shared flag, and that would work for blocking another thread from running at the same time. So we can synchronize like that, and it's a really easy way to control when when two threads might get into trouble running the same code at the same time. So if we look at hashes, there's a hash map, and you'll see a note down here. Note that this implementation is not synchronized. If multiple threads access the hash map concurrently, and at least one of the threads modifies the map structurally, it must be synchronized externally. So this is warning you that there's nothing built into this particular class, right, Hashmap, that controls simultaneous access to the internal structures. And if you imagine any kind of structure, a linked list, a hash, a tree, if two things were trying to make changes to that structure at the same time, you can have chaos, right? Just think of a simple linked list, and one method is trying to delete a node, another one's trying to insert a node. And if you're trying to insert right after a node that's being deleted by another thread, you can get into big trouble. Because if you figure out who should be pointing to your new node, and it's this node that's about to be deleted, and then that node gets deleted, but it's already noted what came after that node, right, your list gets corrupted. So some of these methods or structures will not be automatically synchronized for you, and you have to take care of synchronization yourself. Some of these things, they are synchronized for you. So so hash tables, I believe, are synchronized. Yeah, so unlike new collections, hash table is synchronized. But you can always synchronize things yourself, right? And it's to me, it's good practice to do my own synchronization as much as practical. So threads have a bunch of methods available. So one that's really useful to us is sleep. And sleep basically just puts your current thread to sleep. And you can specify how long you want to sleep, milliseconds or milliseconds and nanoseconds for more precision. So here's a real simple demonstration of sleep. We're going to print out going to sleep. We're going to sleep for 5 seconds by doing 5,000 milliseconds, and then we're just going to wake up and print another message. And sleep is a static, so we run it off of the thread class itself, uppercase thread.sleep, as opposed to constructing a thread. And that's all there is to it, except it can throw an exception, so it's got to go in a try-catch block. So you end up writing this a million times. Like that. So it goes to sleep, waits for 3, 2, 1, 0, and wakes up. So that's useful to do. And you can make it one line if you want.
So how number 1 is 2?
Mm-hmm. Yeah. And Why do you want to sleep? Well, because you've done something and now you're done. And you don't want to exit because something might call typically one of your listeners later, like when someone presses a button. But there's nothing that you need to be doing right now. Well, you could say while true and just sit in an infinite loop. That's really expensive. Right? There's other things the CPU generally can be doing. So if you put yourself to sleep, it actually changes your process state in the JVM. And your job is basically idle until something causes it to happen or until our timer expires. I'll show you some example of that in a few minutes. So sleeping is useful. And threads also have interrupts. So you can interrupt a thread with the interrupt method. And you can test whether the thread's been interrupted with interrupted or is interrupted. The difference is interrupted will actually clear the interrupt flag, whereas is interrupted will just kind of peek at the interrupt flag. So we can do something like this. Let's make a pair of threads. Let's just make one thread. Let's start T1.
I think there's one too many parentheses.
I think you're right. Alright, so we'll start a thread and then we'll just say hit enter to interrupt the thread, and we'll wait for you to hit enter and we'll interrupt T1. And that's our whole program. So here's my thread. Here's our run method. So we'll print a message when we're starting. Print a message when we're done. And let's make a while loop here. So while not interrupted, we'll just sit there and spin in a loop. I honestly don't know if this is likely to work or not. But let's try it. Hey, that's scary. Alright, thread is running, hit enter to interrupt thread. So that thing's in a while loop, where it's looking to see if it's interrupted. I could be sleeping every second if I didn't want to be totally CPU bound. But right now I got Java running, it's taking 107.7% of my CPU. And it's not doing anything, right? Waiting for me to hit enter is not doing anything. But that while loop is totally CPU bound. So maybe that's a problem, maybe it's not. So let's hit enter. we hit enter, and it said hit enter to finish, and then it said thread is done. Did I not do another next line after that? I'll even close my scanner. Alright, hit enter to interrupt thread. So it says hit enter to finish, and the thread is done, and now it's waiting for me to hit enter. And now if I look at my resource consumption, Java's not even showing up. Right, that's Kazam on top, taking all the CPU time. So I can hit enter and that exits. So if I change my while loop, now inside my while loop, I'm going to sleep a second, and that might compile. So same thing as before, and again Java's not even showing up. When I hit enter, interesting. Oh, I got an exception catch. Oh. Okay, I don't want to go down this path. Try one time. All right. So the interrupt actually kicks you out of a sleep, right, which is why we put sleep in a try-catch block. All right. So different good things we can do with interrupts and threads. Let's see.
I bet interrupt is used during the chat program.
I don't think anybody's ever used it, but I've never really talked about interrupts before, so it would make things easier, I think, to use interrupt though. Alright, so Towers of Hanoi. So ignore all of that. This is a J-frame, and we're going to play Towers of Hanoi and do it visually. We're going to show the disks and show them as they move back and forth. And it's not too bad to do. There's a lot of what I call bit flipping in here, right? Just niddly little things where you have to figure out if this is the third disk in size, how big is it? And so if the pole is sitting at this X location, where does the disk begin and end in terms of X coordinates? And stuff like that, and I'm not going to worry about that. I got in a mood and wrote it once, and it works, but it's not topical to threading. But basically, this will let you specify how many disks you want, right, in a text field, and then it'll parse it out as an integer. And I don't ever store the number of disks in a variable. Anytime I want the number of disks, I'm going to call the numDisks method, which is going to look in the text field, parse it as an integer, and return that. So that's good objecting. And the painting is the stuff that gets just like all kinds of magic numbers, and don't worry about that. But basically, I have an array called poles, which stores the number of the disk on each of the 3 poles. So poles bracket something bracket 0 is the number of the disk on pole 0, and so on and so forth. And pole n just tells me how big each of those arrays are. And so this is just magic numbers. We're not going to worry about those, but basically I'm going to draw little rectangles for each disk. And I'm going to set the color based on the modulo of the disk number, mod 8, just so the disks come out different colors. And this is the usual main method you get from Window Builder, and it creates a new towers object. That's what this is, which is a J-frame, and makes it visible, and that's all it does. But I have a number of buttons on the frame, including a go button. Where's my go button? There's my go button. And so the go button creates a new thread off of the class mainFrame, and it runs the start method. And main thread is the code we made in 2.15 for basically playing Towers of Hanoi. So the run method basically does the following. Sets up the initial disks, right? So depending on how many disks you have, it puts the largest disk at the bottom and builds up from there. On pole 0, and then it calls solve, which says solve whatever the number of disks is, moving from pole 0 to pole 1. Pole 0 is on the left, 1 is in the middle. And the solver is just our good old recursive solve. So if number of disks is 1, just move from the from pole to the to pole and you're done. Otherwise, move n-1 disks from the from pole to the third pole, and then move from the from to the to, that's the largest disk, and then move from the third pole back to the to pole, and the -1 disks. And third is another magic function. If you have 2 poles, it tells you what the number of the third pole is. So it's just 3 minus the sum of the pole numbers. And then show move used to just print out what the move is, right? But instead of printing it out, what we're going to do is we're going to populate this array information, and we're going to call save data in that frame, and then we're going to repaint the frame. And then we're going to sleep for a little bit. So save data is just copying over the pole information from the main tower class into these local arrays. And then repaint is going to use those to actually draw the disks. And it's threaded because if I create my main thread and I say run, right, I get my display, and I can put in the number of disks is 8, or I could do 16, right, and so on. But as soon as I say go, everything kind of freezes, right? And it's freezing because I'm sitting inside my main thread class, and I'm doing my pole movement, my disk movements, right? And I'm calling repaint, but repaint does not display this, right? Repaint says when you have a chance, update the display by calling paint. But I'm bound inside my main thread class right now. And unless I have a separate thread, right, that's what the CPU is doing. It's running main thread. And I can't even, like, you know, get out of this by Xing. So if I make that start so that it actually runs in a separate thread, and I say go, then it'll go ahead and it'll start playing the game. And let me put the print back in here. So there you can see what the actual moves are. And so there's a speed option which just affects the delay. So we can speed it up. And it's telling you how many moves you have on the top and so on. And there's a turbo option that just runs full speed. And so that's pretty quick. So we can do 16 discs. And in turbo mode, that's pretty quick. Let's see it again. And 24 discs is not so quick. And it's being slowed down by the output, but it's still really slow. Well, not really slow. It's got a lot of work to do. So it's visibly a long time. But it'll finish eventually. 32, not so much. 64, hopefully not. Right, so if you're doing code and you've got something that's going to be doing a lot of stuff and is never really going to stop doing its stuff, but you still want other things to be able to happen, throw it in a different thread, right? And you can sleep periodically and other things can go ahead and kick in. All right, so interrupts, and there's a join method which says don't do anything until a particular thread finishes. So you can say join on a thread, and when that thread exits, you'll continue. And you can synchronize and so on. And there's all these mechanisms for coordinating behavior among different threads. Managing that, deciding what you want that coordination to be, can be challenging. And there's potential for all kinds of strange things to happen. So this has been studied for a number of decades, going back to the 50s actually. And our favorite mathematician, Dijkstra, was studying parallelism and concurrency in computer systems several decades ago. And he was interested in shared resources on a computer. So for example, you have a computer and it's got a tape reader, and it's got a printer, and it's got a scanner, and it's got something else, right? And you have different jobs running that use different resources. And so classic example, you've got a job that's copying from, say, a paper tape reader to a printer, okay, to make a hard copy of a program. Everybody know what paper tape is? There's what paper tape looks like.
It's like those card readers.
Yeah.
That used to be used for.
Yeah, so this was one long continuous strip, and it had several dots going up and down, and those dots just coded different characters. And you get these things and you'd roll them up and they'd be like really, really long, and you feed one end through and it basically pulls it through, and little...
It's a program.
Yeah, it's a program. Little lights shine through, and if there's a hole, it can sense it, and so on. So it uses an old code called Bordeaux. And occasionally they rip, and then it's like horrible. Because you got to tape it together and pop the holes back in, and so on. So you got something reading the paper tape and copying it to a printer, okay? And you have an operator who's running maintenance tests, right? And is testing different pieces of equipment and printing out a test report. So you start your job, and it allocates the printer, okay, and now it's going to try to allocate the paper tape reader. Okay, well, at the same time, the operator starts their job, and it's running diagnostics. So the first thing it's going to do is allocate the paper tape reader, and it runs some tests and gets the results of the tests, and now it wants to print those out, so it tries to get the printer, and it can't access the printer because your job has the printer. And your job is going to keep the printer until it finishes, and it's not going to finish until it allocates the paper tape reader, does its program, and then exits. And the operator's program is not going to finish until it allocates the printer prints out its report, and then releases the paper tape reader and the printer. And you're deadlocked, right? Both jobs have something the other job wants. And until something changes, right, both jobs are stuck. Well, nothing's ever going to change. And so your system is still running along, other people are coming along and their jobs are running fine, but these two jobs are just locked. And it's a situation called deadlock. So Dijkstra was studying these kinds of things, and he came up with a thought exercise that describes some of these situations. So this exercise today is called the Dining Philosopher's Problem. And so here's the setup. You have 5 philosophers named A, B, C, D, E, and they're sitting around a table, and they're going to eat and they're going to talk. Okay, and you have in the middle of the table an infinite bowl of noodles, so no limit to how much food, and they can eat as much as they want, and they can talk as much as they want. And in between each philosopher is a chopstick. And in order to eat noodles, you have to have 2 chopsticks. And if you've got 2 chopsticks, one in each hand, you can start eating noodles for as long as you want. When you're done, you can put down your chopsticks, you can go back to talking about philosophy. And so the puzzle is, can you describe algorithms to control the behavior of these philosophers such that everybody gets to eat, everybody gets to talk? And it's a fairly tricky thing to do. So your first idea might be, okay, each philosopher picks up a chopstick on their left, and then each philosopher picks up a chopstick on their right, and then they start to eat. And if you do that, philosopher A will get this stick, B will get this one, and so on.
But there'll be nothing on the right.
And then nobody has one on the right, and so they wait.
And the opposite.
And they're going to wait forever. And they're going to starve. So then you can say, okay, so if you don't have a stick on your right, then wait for 2 minutes and try again. Right? That's not going to help. Okay, you could say put down the chopstick on your left, wait for 2 minutes, and then do this algorithm again. Well, if they all started at the same time, they're all holding a chopstick. 2 minutes later, they all put them down, you're back to your initial state. They all try again, you're still back in this situation. That's the situation we would call live lock, right? They're going through different parts of the algorithm, but they're never getting beyond this point in the algorithm, right? So the state is changing, but there's still a fundamental resource contention. And so you can come up with different algorithms and explore what these algorithms do and how well they work and so on and so forth. Now, if you can assign priorities to the philosophers, right, then you can start to find some solutions. If you have a waiter who can come around and say, okay, philosopher B, go ahead and eat for 3 minutes, right, that can solve it. And some of those map well to operating system management, some of them don't. Right? If you know ahead of time what all the resources are and when they need to be used by what processes, you can come up with a schedule. But if these things are being run dynamically, right, you don't know when a certain job is going to need the line printer or the tape reader, right, you can't really schedule it. And so one approach is, for example, you can number the chopsticks. And you can say everybody picks up the lowest numbered of the 2 chopsticks first, and then and only then pick up the other chopstick. And so if you do that, philosopher A is going to try to get chopstick 1, philosopher B is going to try to get chopstick 1. Okay, so one of them will get it, the other one won't. So let's say philosopher B gets this. Well, philosopher C is going to get chopstick 2, and nobody's competing for that. Philosopher D gets 3, philosopher E gets 4. They get their chopsticks with no competition. But one of either A or B will succeed and the other will fail. And then you say, okay, now pick up the other chopstick. And since nobody's after chopstick 5, if B got their chopstick right, E will succeed. If A got their chopstick, they're going to try to get chopstick 5, but nobody's getting chopstick 1. Yeah, so if I've only got 30 seconds. But if you play through this, the end result is at least some of the philosophers will be able to start to eat. And they eat for a certain amount of time, and then they put their chopsticks down and wait for, eat for 2 minutes, wait for 5 minutes, and that gives a chance for others to get their turn and so on. So you can start coming up with algorithms like this, but this is a classic problem. You'll study this a lot in other courses on operating systems and system programming and such. But it's something I just wanted to touch on because you'll definitely see it again.
Are there, like the opposite of a greedy program, is there a solution for it where it's like the first step is to tell it to give, like an altruistic program?
Yeah, you can do that.
The very first step is for you to grab a chopstick and give it to someone else?
Yeah. There's probably variations of that would work well, yeah. Or like, if you have one chopstick and you can't get the other one, then you give them both up. And yeah, if you identify the philosophers, you can do other things. If you prioritize them, you can do things.
That's cheating.
Yeah. All right, so tomorrow I want to start talking about sockets and network communication, client-server stuff. And we'll start playing around with that. And that'll move us to talking about PA5 on Friday.
Today I'm attended.